Well, let me just get started. Make sure the stream is up. If it is up, let me just start recording. Okay, we are live. So, let me go to that stream just in case I miss any chat. Okay. Where's the Desmos thing that I was looking at? Yeah, right here. Okay. So, we left off yesterday. We got the whole SAT working, the separating axis theorem working, where we were determining overlap, like the best edge or the overlaps right here. When they're not intersecting, there's negative overlap. When they are intersecting, there's positive overlap. So the next step is that we now need to determine all the edges and the contact points involved, because we want to plug this into an impulse solver, and just detecting if two shapes overlap isn't enough. We need to determine the contact points and the normals to resolve with, and the penetration, the separation to push out. Lots of stuff we got to figure out. So we'll just get started. Let me, this can work. Yeah. We change this to y, x, y, x. That's the order in which we define the normals. Like the first normal on box 1 is pointing down, so that's going to be y. The second normal on box 1 is going to be pointing to the right. That's going to be x. Just changing these variables around. Gonna get rid of these. And so now we have a concept of a reference box and an incident box. The reference box is going to be the box which provides the separating axis, the minimum separating axis. So if we were to overlap on this, in this orientation, the minimum axis would be the x-axis. And you can see right here, best edge index, like the best edge to separate along, the piecewise function returns 2 for the x-axis of B1. So we can plug this into another piecewise function. We're just going to be using, in Desmos, you don't have if-else statements, you just have piecewise functions to work as conditional logic. And that works well enough for us once you get comfortable with it. If you're not comfortable with any of this, then you can look at my Desmos tutorial stream. Or you can just keep following along and pause where you need to and just do as I do. So we're going to call it RB for reference box, and we'll say if best edge index equals 1, we'll give box 1 as, you just do 1 as the best box, the reference box. If best edge index is 2, it's still 1. And then if it's 3 or 4, then we use box 2. And then IB, the incident box, we're going to have the reference box and the incident box. And this will basically do the same thing. Well, I don't even think, yeah. We don't need the number for it. We just need the positions now. So we do like RBP, reference box position, equals then another piecewise function. Reference box is 1. We will give it box 1. Otherwise, it'll be box 2. And the same thing for the incident box. Incident box position, if reference box is 1, then we'll give it box 2. Otherwise, it'll be 1. And then we can also label these, and we can call it reference box or ref, and then incident box or inc, right? So in any orientation in this setup, because they're both axis aligned, we're just going to pick the first box which yields the best axis. And in this case, it's always going to be box 1 because that's just the way the piecewise function shakes out. So now we can determine the reference and index boxes. Now let's just generate all the vertices. So we're going to do reference verts, and it'll be the same thing if reference box is 1, we'll return B1 verts. Otherwise, we'll get back B2 verts. I'm going to repeat this for the edges. Reference edges and reference normals. We just call it RN, reference normals. This will be B1N, B1 normals, or B2 normals. And we will repeat this for all the incident information. So instead of RVerts, we'll call it IVerts. If reference box is 1, then we'll return B2 verts. We'll just flip these. Same thing for edges and normals. Okay. So, an important thing to remember, one of the subtleties in the ways in which I did the separating axis theorem, this can work with any arbitrary polygon shape as long as it's convex. And convex just means if you shoot a line through any entry and exit of the shape, it only passes 2 times. So if it's like converse, I could draw it. Yeah, I'll just draw it. Paint. So this is a convex shape, right? Kind of. You can pass a line through. Oh man, that is a horrible line. And you see that it only intersects twice, right? Whereas a non-convex shape, you pass a line through and it intersects more than 2 times. If you want to break down any non-convex shape into a convex shape, you can separate it into more shapes. So like you can cut this into multiple triangles, or like a square and 2 triangles, and then you can like pass lines through and it still works, right? But we're only caring about squares for right now. That's all I care about for my engine. And the separating axis theorem works for any convex shape, and the square is a convex shape that's arguably simpler than the triangle. For 2 dimensions at least. So that's what we're using. And so as a consequence of using that, I can color code it again. Let me fill this in. I really do need a drawing tablet. I feel like orange and blue. So just use lines, right? So the edges of this box with the same colors share the same normal, right? That is terrible. Even though they're pointing in different directions, you know, this is negative x, negative 1, 0. The other one is positive 1, 0. They're still pointing like along the same line, right? They're still pointing along this axis. And the same for the blue faces. They're still pointing along this axis, right? And so what we can do is that instead of comparing every vertex against every single edge, all 4 edges, we can break it down and just compare against 2 edges which have the same axis. But in doing so, we lose the full information of the exact direction of the normal that we want to resolve with. So this next step is very simple, and it's just to reconstruct that data that we lost when we only project against 2 of the axes. When you're doing a more complex shape, like a hexagon, can we make a hexagon? 1, 2, 3, 4, 5. You're just gonna project every single vertex along every single normal, and so you won't lose any data. But we're cutting some corners for the square case. It'll make more sense if you just do it on your own. So to do that, we're just going to take D, like the difference between the 2. We're going to do incident box position minus reference box position. And we're going to dot it with the axis, the best axis that we're separating on, the separating axis. if you will. And we also need to find that. So we can take man, I'm drawing a blank here. Okay. The axis. We're going to find the axis. And that'll represent the best edge to separate on. So this will be another piecewise function. We'll do best edge index. If it equals 1, then we're going to take B1 normals, the y from the by normals, the x from the by normals if it's 2. Same thing here, but we'll take box 2. 4. Okay. It's undefined because I did something wrong. The best edge index is 2. BI equals 1. BI equals 2. Oh, yeah, I fucked that up. Equals 3. There's going to be a lot of mistakes in this stream. It's going to turn into a total disaster. We got to keep trying. Oh, God. Okay. So this gives us the best axis to resolve with. And in this case, it's 1, 0. It's pointing, in my case, to the right. If I'm pointing at the camera, then it's this way. That's the axis that we want to resolve along. You see that's the x-axis. We'll push out that way. We're going to... It's like the direction we're pushing the incident box in. Yes, okay. Yes, they share the same axes. Okay. So you see that even though it's 1, 0, we're going to think that we're going to need to push the incident box to the right, which isn't correct, because this is what I was talking about when I said that when we only take those two axes, we lose the absolute direction. Like it could be either -1 or +1, but because we collapse both those axes into one, we're just going to return +1 every time. So in order to correct that, we need to take the dot product between the difference between the boxes with the axis. And if it's less than 0, then we need to flip the axis. It's going to be piecewise. Do like a collision axis, right? Or collision normal, or yeah, we'll just call it collision normal. This is now the normal that we're going to use to resolve this collision. And then you see when the reference box is to the right of the incident box, we're going to push the incident box left, which lines up with -1, 0. When it's on the left, it's going to push it to the right, which lines up with 1, 0. When it's on top, it's going to push it down, which works with 0, -1. And when it's underneath, it's going to push up, right? So we now have the correct normal to use. And now we need to find the edge, the edges involved in this collision. Because right now, you know, there's 4 edges on the squares. We don't know which one is involved in the collision. So we need to pick the edge which is most aligned, or the edge with a normal which is most aligned with a collision normal. And we can do this by, let's start with the reference edge. Reference edge equals, or we can do like reference edge index, REI, reference, I'll just make it verbose for you. Reference edge index, no, we'll just take best reference, best edge. The edge that best aligns with the collision normal. And that will be the maximum value of the dot product between the collision normal and all the edges. And then we'll do R best edge index equals, this will be piecewise, and we'll just compare every single one. Best edge equals R edges 1, or return 1, 2, 3, 4. I'm doing something wrong, as usual. What am I doing wrong? Cannot compare a number to a point. Oh yes, okay. I need to dot each one with a... Okay, there we go. Need to dot them all with the collision normal. Okay. So this gives us edge 3. So edge 1, 2, 3. I don't think that's right. Best edge. It should give us edge 4. This is edge 1, 2, 3, 4. I get something wrong every step of the way. This is going to take a while. Let's just see what each one of these is. The collision normal is -1, 0, dotted with our edge. Oh, I was doing it wrong. We need to take the normals, not the edges, the normals. The axis, the best separating axis is one of the normals that we get from the edges. And the normals are perpendicular to the edges, so we want to use the normals. Sorry about that. So we're going to use Rn for normals. Rn. Okay, now it's looking correct. Okay. So, our best edge index returns 4. And so we'll get our edge equals reference edges, our best edge index. And this will give us 0, -2, which lines up with this edge right here. Because the direction of that edge is going, there's no x component, it's just going down -2. And so because the vertices that we use line up with the edge indices, we can also do the same for our vert, the reference vert. We can do r verts, and we'll do r best edge index. And so you'll see that that's the reference vert. We'll do reference vert. And now we can do the same for the index. No, the incident vertex and the incident edge. Let me just draw this. So we're going to draw a line, and we'll start at the reference vertex, and we'll go from the reference vertex plus the edge. And then we'll color it pink. And then you see that this edge right here is what we're going to use to determine the contact points. And you can see that for any orientation, it always faces the box that we're colliding with. So this is correct. So now we're going to do the same for the incident edge. And the incident edge is going to need to, we're going to compare the axis or the collision normal against the incident normals, and it's going to need to oppose. So now we're going to need to swap the normal around. So I'm going to take the maximum between the dot product of IN and the collision normal. Call this I best edge. And so then we'll compare them all again. We do I best edge index I is for the incident box. We'll do I best edge equals negative Cn dot I normal 1. It's going to be 1, 2, 3, 4. And you see that it's 2. We'll plug that in. We'll do I edge equals I edges I best edge index. Do the same for vertices. And we'll label them. And we will color these green. And we'll draw it. Just copy this and, well, now I need to copy that. Ivert plus I edge T. I'll color it green. And we'll label the vertex, call this Ivert. So now you can see that we're correctly coloring the edges involved in the collision. These are the edges that we're going to clip the points along. And so this will also account for orientation of the boxes. We can rotate the box a little bit, make things look super messy. And you can see that they still correspond. We have, remember, the reference box is the box which gives us the axis, which is the axis in which we need to push along the smallest amount to separate the two boxes. And the incident box is what we're pushing out. And you see that in any orientation, they're always going to overlap each other. Pretty cool, right? Let's undo that rotation. And now the next step is just clipping. So in order to do this, let's check out this article again. Contact points using clipping. An article from 2011. Imagine that. Oh my God. But it does it in a similar process. We aren't using arbitrary edge polygons. We're just using squares, so this is going to be simpler for us. But the same concept applies. I've linked it in the description of this video. But this is what we care about right here. This is how we get the clipped points. We're going to feed in the incident vertices, and then we're going to clip those, and then we're going to feed back in those clip points, and we'll do this in a Desmos way. And I just need to remember how to get O1. O1 is the dot product between the reference edge and the vertex. Reference vertex 1. Okay. Yes. This is our edge dot our vert. Just say O1 equals our edge dot our vert. Well, we can do RV1, reference vert 1. That'll be the same as a reference vert, and then we'll have RV2. We'll color these pink, and we'll also label them. This is going to be the reference vert plus the edge. Because that'll go all the way along that line and end up at the other vertex. Well, this RV1, RV2. Not doing it right. Our edge. Oh. No. Edge. Okay, there you go. So now we can see the reference vertex 1 right here and the reference vertex 2. We can stop drawing like our vert right there. Do the same for ivert. And we will do the same for incident vertex 1 equals ivert. And ivert 2 is going to be ivert plus I edge. Color these green. Gonna label them. You can see that we now have incident vertex 1 and incident vertex 2 along that edge, and they swap with whatever orientation we have. And so now we're going to start projecting along these edges. So we're going to do O1, and then that'll be RV1. O2 will be RV2, I think. Yes. And now we are going to get the distances along the axes. And we can do that with dotting, like distance 1 equals the dot product between the collision normal. I think it's the collision normal, or is it the edge? I think I have this wrong. It'll be the edge. Between the reference edge and the incident vertex. IV1 minus O1. Let's see if that makes sense. Yes. Okay. Because we're clipping what's happening, you'll see it once we start drawing it, but we're just clipping the incident vertices along the reference edge. This is the clipping step. So we'll do the same for D2. Just make sure that it's the right thing in this article over here. D2 equals the dot product between the reference edge and vertex 2 minus O. Okay. Okay. And then we'll do clipped point 1, CP1 equals, we'll just call it like 1, like for the first step, the first clip point of the first step, CP11. We'll give the piecewise function if D1 is greater than or equal to 0. We're going to feed in incident vertex 1. Otherwise, that means that the distance when we clip incident vertex 1 along the reference edge is going to be less than 0, so we're going to feed in the second vertex here, IV2. What are we doing wrong? D1 is less than, it's greater than 0. Don't understand the dot here. Oh, it's because I need to add a comma there. Okay. So we can label this. This is CP11. And you can see that it always lines up with most of the time with incident vertex 1. We'll do the same here. We'll do like CP12. The first clipping step. So this will either be if D2 is greater than or equal to 0. You need to do like D1. This will require both D1 and D2 being greater than 0. This will be IV2. Otherwise, this is where we start getting a little silly. So, remember, we're clipping incident vertex 1 against the reference edge. And if one of them is outside of bounds, so they both line up with the reference edge right here, but when the box moves down, we're going to need to start clipping incident vertex 2 to the edge. I think I have them swap from, yeah, okay. Okay. Let's keep it like this. This is a bit more straightforward for me to understand. So incident vertex 2, it's now on the bottom, and you can see that when it crosses under the edge, D2 goes negative, and that means that they're on either side of the box, so we need to clip one of the sides. And so we do that. We reference this article. We're going to start stepping along that line. So when D1 and D2 are on opposite sides of this axis, multiplying them together will be negative. You know, multiplying positive with a negative is going to be negative. And in that case, we're going to need to project the clipped point along the reference axis. And we do that by taking the incident edge and multiplying it by D1 divided by D1, D2. We'll call it U equals, or U1, since it's from the first step, D1 over D1 minus D2. And then we'll do, God, it's getting hard to name these. I don't know, clip point 1 pos, like this is the position of the clip point. Yeah, why not? This will be IV1 plus, remember this is another like stepping along the line thing, so we're starting at the first vertex, we're adding the slope, then we're multiplying it by U1. And then we label it, we'll call this clipped pos 1. And you see, I mean, it's always going to be that, but you can not draw that. And only if this has been clipped, then we start drawing it. So CP1 pos. We'll call this clipped pos 1. And so then you see that when it's above the reference edge, it'll always be at incident vertex 2. Otherwise, we'll clip it. It'll always lie along that vertex. So from this step, we have two positions, and we're going to feed them back in. And so we'll just repeat that process. So we have, yes. So now I'll have like D11 equals, we're going to reverse this now, because now instead of stepping along the reference edge in one direction, we're going to step along in the other direction to see when the other point is outside of the reference edge. And so we're going to feed it CP11 minus O2. I think that's right. To reference this code over here. Yes, the negative reference edge. Going to feed in those clip points, and we're subtracting by negative O2. And minus O2. Same for this. This will be P12. Call this D21. This is the second clip step, and D22. And so now we're taking a look at this top vertex over here. And you can see that when they're both on one side of it, they're both positive. But when incident vertex goes above it, they flip again. And so we're going to need to do the same thing, where we can just call this clip point 2. And we can say if D21 is greater than or equal to 0, we can feed in incident vertex 1 or CP11. Or it's going to be CP12. Draw it. And I don't think that's right. 2. That's the second clip point that we're feeding in. IV2. This is a disaster. So I'm drawing a blank here. So we're going to open up this other implementation that I got working this morning. This whole implementation, we're going to figure out where I went wrong. Clip point 2 is going to be CP2 minus the first edge. Where's CP2? I'm getting totally lost. There's so many steps. It's a terrible educational stream, by the way. Yes, I see where we're going wrong. Okay. So it's either going to be greater than 0, and if it's not, that means they're on opposite sides, and so we're going to do the same thing and calculate U2, which is going to be D21 over D21 minus D22. And then we're going to go CP2 pause equals, and this will be IV1 plus I edge times U2, if I'm not mistaken. And that'll be clip pause 2. Clip pause 2. And you can see that that's where it ends up. And we'll feed it in here. CP2 pause. Let's not draw that. Let's call this clip pause 2. And we'll label it green. Color it green. Okay. And you can see that they both line up. They're always going to be contained. They're clipping to the reference edge. That's what all these steps were. Where we check if it falls along that edge, and then we clip it to fall within that edge along the incident edge. And these are our contact points. And so, let's see what happens when we rotate these. Let's rotate the boxes a little bit. See if we get a huge mess. Okay. Pause 2. Okay, and you can see that they fall inside the axis, the reference edge. Yes. Yes. The reference edge is pink, and we just need to make sure they fall inside of it. But in some cases, you know, clip pause 2 falls outside of this. So we need to do one more test where we take like the CP1 final, and what we're going to do here is we're going to check if it lies within the box. And to do that, we're going to take, we'll do CP1 minus the first reference vertex dotted with the reference edge. If it's less than 0, we're going to, yes, that means that it's inside, it's penetrating, and so we'll give it CP1. I'm doing this wrong. Cannot subtract a point from a number. It is because let's just undo the rotation. Clip pause 1, clip pause 2. Take CP1, 2. Okay, and I think I had it backwards. It's going to be greater than 0? Oh. Less than. Greater than 0. Why does that give us... That is bizarre. Clipped pos 1 falls inside the reference edge. It's going to be less than 0 when we dot it with that edge. Or no, I'm thinking of reference normal. Gotta do the reference normal, right? Reference normal? What did I call it? I'm getting all confused. Reference edge collision normal. Dot it with the collision normal. We need to wrap these in parentheses. Oh my god. What the hell? Okay, well, let's just pull this out and see what the deal is. Dot CN. Collision normal. Yeah. Okay. I don't know what the problem is. Oh, that's because... Yes. Okay. That's because I wasn't feeding in the right variable name. Okay. So we'll stop labeling these. We'll call these like CP1 final. This is the final clip position because we're just checking if it falls within the reference edge. And we'll do the same for the second one, which is CP2. Call this CP2 final. So, stop labeling CP1. We'll rotate these again. And then you see CP1 here, CP2 here. As soon as one of them falls outside that reference edge, we stop drawing it, which basically clips it again. So now we only have one contact point for the first clip point, and when it interpenetrates the reference edge, we have the second one for any orientation. You see that? When the reference edge passes the point where the clip point 1 is, we start drawing it. Otherwise, we pull it out a little bit and we only have one contact point to resolve from. So we now have the normal. Remember, the normal is Cn. Can I like draw or label it? I don't know, whatever. Cn is the collision normal that we're going to feed into the impulse solver. The contact points are CP1F and CP2F. And so the last thing we need is a separation, like the amount that we need to resolve. And we can get that by basically doing this again. We can get the, well, this will give us the penetration, but let's cast it. Like, let's get, just to demonstrate where the corresponding points are on the surface of the reference edge from the clipped collision point. Like, we're going to cast it in that direction along the reference edge and see where it falls. And so to do that, we're going to do the same thing. We're going to do like CP1F surface. This will be reference vert 1 plus reference edge times, and then we're going to need to use T. And T will be, yeah, we can just do it this way. We'll just do CP1F projection. And we'll do like reference edge 2, reference edge squared. This is R edge dot R edge. Reference edge squared. The projection will be CP1F minus the reference vertex. Put this in parentheses. Dotted with the reference edge, divided by reference edge 2. I don't think, oh no, that is right. Yeah, that is right. It's 0 because CP1F is here, and that lines up with exactly the start of the reference edge. And we'll do the same for second clipped surface point, CP2F. And then we'll draw them. CP1F projection, CP1F projection, and CP2F projection. And this will be the projection of the first clip point on the surface, CP1 surface. This will be the projection of the second clip point on the surface, CP2 surface. There you go. You can see that, move the box around. If we stop drawing it when they fall outside, there you go. And then we can also determine the penetration with this exact thing that we tossed in earlier. So we can do a CP1 penetration or separation. And same for CP1. Yeah. CP1 separation, CP2 separation. Final. Put that F in there. And so that'll give us the separation that we want to plug in to the impulse solver. So we have the contact points, we have the normal, and now we have the separation. And it should work with any orientation of these boxes. And I can add more rotation. We can scale them. Let's like make one of them larger too. Let's rotate these a little bit more. Here's the reference edge, and so you can see that we're still drawing the correct surface positions, the contact points. We move it around, we still clip them correctly. So this is, I mean, it looks really silly because we're drawing so many lines everywhere, but this is the full separating axis theorem with point clipping for 2 dimensions for any oriented squares. We're only doing squares. We're not doing arbitrary polygon shapes, but the same concepts still apply, where you determine the minimum separating axis, you figure out which edge on the shapes correspond to that axis, and then you clip points against each other. And that's it. And with this, you can see that we're going to push away from the reference box. We have the surface points and the collision points, and we're going to like slide them through once we plug in that information in the impulse solver. So the next step is just feeding this all into C code and getting it to work, because like, I mean, this is just a snapshot in Desmos of like a single frame of what the solver would look like. So yeah, next step is just feeding it into C, and I guess we'll figure that out at some other time. I know I didn't really do a good job of explaining all this exactly. I linked the article. You can just use all this math. You can see that it works. And the confusing part for me was just keeping track of all the different variable names and the piecewise functions in Desmos. Desmos is a bit trickier than C. You know, C you have if else statements. And then it's just a matter of projecting the points along the surface of the reference edge and then clipping them. And it works. So, how long have we been going? We did this second part. I thought it would take a lot longer, but we did it in less than an hour, and we have the full separating axis theorem in Desmos. Look at that. Isn't that beautiful? And I'll leave the link in the description. The link's in the description. The reference article's in the description. That should be everything. Jack Mixon. OMG, hi Nate. Hi Jack Mixon. How are you doing? Wow, he might be the only other viewer. Did you enjoy the separating axis theorem? I hope you did. If you want to learn more, you can just recreate it in Desmos like I just did and read that article. Next time I stream, we'll be doing this in C, but until then, let's try and, it would be nice to get it working and see before the new year. So we got like one more day. That would be nice. But I got nothing else to say. We can like rotate them a bit more, just test for more orientations. Yeah, it looks right. Looks good to me. Cool. Okay, that's all I got. Thanks for watching. I'll catch you next time, people.